The Quantum Zeno Effect is a fascinating phenomenon in quantum mechanics that essentially states that a system's evolution can be hindered or frozen by frequently measuring it. An analogy: the flickering light bulb. Imagine you have a flickering light bulb that can be either on or off. It switches states randomly at a fast pace. Without observation, if you don't look at the bulb for a while, it will keep switching between on and off states. When you finally look at it, you see it either on or off, but you missed all the switching in between. With frequent observation. Now suppose you decide to check the bulb's state every second. Each time you look, the bulb might be forced to stay in the state it was in when you looked. If it was on, your observation can freeze it in the on state for that moment, preventing it from switching to off, and vice versa. In quantum mechanics, the frequent measurements act similarly. By measuring a system often, you keep collapsing its wave function to the state it was in at the time of measurement, thereby preventing it from evolving into another state. The Quantum Zeno Effect represents one of the most intriguing phenomena in the realm of quantum mechanics. It posits that frequent observation of a quantum system can prevent it from evolving, in essence, freezing it in time. This concept, which sounds like something straight out of a science fiction novel, is a real and measurable effect with profound implications for our understanding of the quantum world. To visualize this, consider Schrödinger's cat, a thought experiment where a cat in a sealed box is both alive and dead until someone looks inside. In the context of QZE, frequent checking or observation of the cat would theoretically keep it in one state, alive or dead, thus preventing it from shifting to another state. A more mundane analogy might be checking a cake repeatedly while it bakes. Each opening of the oven door lets out heat, potentially affecting the baking process, akin to how observation affects a quantum system. The Quantum Zeno Effect was first formulated by physicists Baidyanath Misra and George Sudarshan in 1977. They proposed that a quantum system's evolution could be hindered by continuous observation, an idea that challenged traditional notions of quantum mechanics. This theory sparked considerable debate and further research into the nature of quantum measurements and their effects on physical systems. Historically, the concept can trace its roots back to earlier thought experiments in quantum theory, which hinted that observation could influence quantum states. These models set the stage for the formal articulation of the QZE. Drawing an analogy from classical physics, consider Galileo's inclined plane experiment, where rolling balls measured the rate of acceleration. If Galileo had made continuous measurements in a quantum sense, he might have influenced the ball's behavior, similar to how QZE describes quantum measurement influencing particles. Quantum measurement plays a crucial role in the Quantum Zeno Effect. In quantum mechanics, the act of measurement causes the wave function, a mathematical description of the quantum state of a system, to collapse to a specific state. This collapse is central to how observation affects quantum systems under the QZE. A classic illustration of this concept is the double-slit experiment, where electrons pass through two slits and create an interference pattern on a screen. If one observes which slit an electron passes through, this knowledge collapses the wave function, and the interference pattern changes dramatically. Analogously, taking a snapshot of a moving object captures it in a single state of motion, altering our perception of its continuous movement, much like how a measurement in quantum mechanics alters the state of a system. The Quantum Zeno Effect is not just theoretical, it has been demonstrated experimentally with various quantum systems. One of the landmark experiments was conducted by Wayne Itano and his team in 1990 using beryllium ions. By frequently measuring the quantum state of the ions, they were able to significantly slow down transitions between states, effectively demonstrating the QZE. This experiment can be likened to stopping a clock repeatedly. Each stop halts the progression of time momentarily, and when done frequently enough, can give the illusion that time has nearly stopped. This analogy helps in understanding how repeated measurements in the Itano experiment hindered the natural evolution of the quantum state of the ions. The mathematical description of the quantum Zeno effect is grounded in the principles of quantum mechanics, particularly the projection postulate. This postulate states that the action of measuring a quantum system forces the system into one of the eigenstates of the measurement operator. When such measurements are made frequently over a period, the system remains in its initial state, demonstrating the QZE. To visualize this, imagine a surveillance system monitoring a restricted area. Each check acts like a quantum measurement, ensuring that no alterations occur within the monitored zone. This continuous observation keeps the system in its initial undisturbed state, analogous to how repeated measurements keep a quantum system from evolving. In the realm of quantum computing, the Quantum Zeno Effect offers promising applications, particularly in the stability and control of quantum states. Through frequent measurements, quantum computers can potentially stabilize qubits, quantum bits, the fundamental units of quantum information, against decoherence, thus preserving the information stored in them. This can be compared to debugging software, where developers frequently check code for bugs. Each check can prevent the software from executing errors, similar to how observations in quantum computing can prevent errors in quantum calculations by stabilizing qubits. Quantum Zeno Effect versus Anti-Zeno Effect. While the Quantum Zeno Effect describes how frequent observations can freeze the state of a quantum system, the Anti-Zeno Effect suggests the opposite. Frequent observations can accelerate the state change. Experimental evidence supports the existence of both effects under different conditions, demonstrating the nuanced interplay between observation and quantum state evolution. Consider, for instance, a security guard on patrol. If the guard checks in frequently, an intruder might manage to sneak in, illustrating the Anti-Zeno effect. However, if checks are constant, the intruder's progress is hindered, akin to the Quantum Zeno effect. This analogy illustrates how the frequency of observations can either prevent or accelerate changes in a system. The applications of the Quantum Zeno effect extend beyond theoretical physics into practical technologies such as quantum cryptography and advanced sensor systems. By utilizing the principles of QZE, technologies can achieve greater stability and security. For instance, in quantum cryptography, frequent measurements can be used to detect any eavesdropping by noting disturbances in the quantum state of the transmitted information. This principle is akin to frequent inspections in a manufacturing process, which ensure the quality and integrity of products. Just as these inspections prevent defects in products, frequent quantum measurements ensure the security and correctness of information in quantum cryptography. The Quantum Zeno Effect raises deep philosophical questions about the nature of reality and the role of observation. Thought experiments like Wigner's friend explore these ideas by considering scenarios where different observers might have different accounts of a quantum event. This leads to questions about the objectivity of reality and whether it is shaped or even determined by our observations. These philosophical debates are similar to discussions about whether a tree makes a sound if it falls in a forest with no one to hear it. Both scenarios question the relationship between observation and reality, suggesting that what we perceive might be as influential as the physical events themselves. There is growing interest in exploring whether the Quantum Zeno effect could play a role in biological processes. For instance, enzyme reactions and neural activities might exhibit quantum behaviors that could be influenced by observation, akin to the QZE. Research in quantum biology is investigating these possibilities, though this field is still in its infancy. A relevant analogy here is the effect of constant medical monitoring on a patient's treatment. Just as frequent checks can alter the course of medical care by providing real-time feedback, frequent observations at the quantum level might influence biological processes in ways we are only beginning to understand. The Quantum Zeno effect challenges our traditional concepts of time by suggesting that continuous observation can affect the temporal evolution of a quantum system. This has implications for our understanding of time itself, potentially offering insights into why time appears to flow in a single direction and how it might be manipulated. In everyday life, the perception of time can be influenced by focus and anticipation. For instance, time seems to slow down when we are intensely focused on a task, similar to how frequent quantum observations can slow the evolution of a quantum state. This analogy helps bridge complex quantum concepts with relatable human experiences. Quantum optics, which deals with the behavior of light and its interactions with matter at the quantum level, provides a fertile ground for observing the Quantum Zeno Effect. Experiments involving optical cavities, quantum dots, and entangled photons have all demonstrated aspects of QZE. These studies help illuminate how light behaves under constant observation and the potential applications of these behaviors in technologies like lasers and optical computers. A simple analogy can be drawn with the function of a camera that captures light. Just as frequent snapshots can alter the way a camera captures images, frequent measurements in quantum optics can change the way light interacts with matter, potentially leading to new technological applications. Despite its fascinating implications, the Quantum Zeno Effect is not without its challenges. Practical issues such as the difficulty in isolating systems for observation and the technological limitations in measuring quantum systems accurately pose significant hurdles. Additionally, theoretical questions about the boundaries and scalability of QZE remain largely unanswered. These challenges can be likened to the difficulties faced in maintaining a perfectly controlled environment in practical scenarios, such as cooking a delicate recipe or managing a sterile environment in a clean room. Just as these tasks require precise control and conditions, effective utilization of the QZE demands exceptionally high standards of experimental setup and execution. In the fields of chemistry and material science, the Quantum Zeno Effect has potential applications in controlling chemical reactions and influencing material properties at the quantum level. By manipulating the frequency of observations, scientists can potentially direct the outcome of chemical processes or alter the material characteristics desired for specific applications. This concept can be compared to quality control in pharmaceutical manufacturing, where frequent inspections ensure the consistency and efficacy of drug production. Similarly, applying QZE principles could allow for precise control over chemical reactions, enhancing the quality and performance of chemical products and materials. Quantum thermodynamics explores the non-classical behavior of heat and energy at microscopic scales. Here, the Quantum Zeno Effect has intriguing implications, particularly in the control of heat transfer and energy flow in quantum systems. This could lead to the development of quantum heat engines or refrigerators that operate under principles fundamentally different from their classical counterparts. One could compare this to the control of energy use in household appliances, where frequent interventions, such as adjusting a thermostat or regulating a refrigerator's compressor, can lead to more efficient energy use. Similarly, by employing QZE principles, one could theoretically optimize energy flow in quantum devices, enhancing their efficiency and effectiveness. The Quantum Zeno Effect itself presents a paradoxical situation. By merely observing a system frequently enough, its natural evolution can be halted. This phenomenon seems to contradict intuitive expectations about how physical systems behave and challenges some foundational principles of quantum mechanics. This paradox can be likened to the everyday saying that a watched pot never boils. While in the classical world this is obviously not true, the Quantum Zeno Effect makes a similar phenomenon a reality in the quantum realm. This analogy helps illustrate the counterintuitive nature of quantum mechanics and the intriguing puzzles that it presents. Decoherence refers to the process by which a quantum system loses its quantum properties as it interacts with its environment, effectively becoming classical. Decoherence is a major challenge in realizing practical applications of the Quantum Zeno Effect, as it tends to disrupt the conditions necessary for maintaining a system in a quantum state through observation. The challenge of maintaining focus in a noisy environment serves as a useful analogy for understanding decoherence. Just as it's difficult to concentrate on a task with constant distractions, it's challenging to maintain a quantum system in a coherent state when it is being bombarded by environmental interactions. Frequent observations can help reset the system, akin to refocusing one's attention, which is essential in managing the effects of decoherence. Quantum Zeno dynamics, or QZD, is an extension of the Quantum Zeno effect, focusing on how dynamic changes within a system are influenced by frequent measurements. This aspect of QZE offers new ways to manipulate and control quantum systems, crucial for advancements in quantum computing, quantum communication, and other technologies. The analogy of fine-tuning an instrument, such as calibrating a piano to achieve perfect pitch, illustrates the precision required in QZD. Just as subtle adjustments in tuning can significantly affect the sound quality, small changes in the measurement frequency and type can dramatically influence the behavior of a quantum system under QZD. As we explore the depths and implications of the Quantum Zeno effect, it becomes clear that this phenomenon holds keys to unlocking mysteries of the quantum world and advancing technological frontiers. The ongoing research is likely to yield more surprising insights and applications, potentially revolutionizing fields such as quantum computing, quantum cryptography, and quantum sensing. The evolution of the Quantum Zeno effect could mirror the historical development of other major scientific theories such as relativity or quantum mechanics itself. Each of these theories transformed our understanding of the universe and led to technological breakthroughs that were once unimaginable. Similarly, as our understanding of the Quantum Zeno effect deepens, its full potential to impact science and technology might only be limited by the extent of our imagination and the depth of our inquiries.